All right, in this lesson, we are going to be talking about differentiability. So, we introduced this word differentiable in our last lesson, and the word differentiable means that the derivative of f exists at a certain point at x equals c. All right, so in order for the derivative to exist at x equals c, the graph of f must have local linearity there. All right, and that's just a fancy way of saying, like, if you were to zoom in on the graph really, really close, that it would look like a line on the graph. All right, but that line would also not be a vertical line because a vertical line has its slope is undefined, and since a derivative is a slope, we don't want to have an undefined slope there. All right, so there are four ways that you can look at a graph and determine if a function is not differentiable. Okay, so the first one is a sharp turn. So if a function like an absolute value function is a good example, if a function has a sharp turn right there, then we would say that the function, so I would be able to say f of x is not differentiable at x equals 2 because there is a sharp turn there. Okay, and notice that I identified the location where this happens. That is because f of x is differentiable at every other point. I can pick any other point on this function, and the function would have a derivative there. Okay, remember a derivative is a slope, and so I can identify the slope of this line, and this line, and this line. All right, and over here, this line, and this line, and this line. The only place where I can't identify a slope is right here at x equals 2. And the reason for that is remember that a derivative is a limit, and limits must be equal on the left side and the right side. So if I identified the slope on the left side of 2, I would have a slope of -1 right there. But if I identified the slope on the right side of 2, I would have a slope of +1. So the limit on the left does not equal the limit on the right, or the slope on the left does not equal the slope on the right. Therefore, the function f of x is not differentiable at that point. All right, number 2, f of x has a discontinuity. So one type of discontinuity is a vertical asymptote. It could be a jump discontinuity, or it could be a hole in the graph as a discontinuity. So f is not differentiable at x equals 2 because there is a discontinuity at x equals 2. All right, so I did not realize that what I just wrote up here was actually written down here already. All right, and f is differentiable for all other values x. So same thing over here. F is differentiable for all other values. So any other point that I pick, I can draw a tangent line there, and I can get a slope. All right, so I want to talk a little bit more about this because there's a very important connection that I want you to be able to make in future problems. Okay, so back in geometry, you learned about conditional statements. So you would say, like, if P, then Q. And you might write those like this: if P, then Q. Okay, and then you learned 3 others. So this was the conditional. All right, and then there was the inverse. The inverse would be the negative version of that. So you would say, if not P, then not Q. Then there was the converse, and that's where you just switch the original one. So that would be if Q, then P. All right, and then what you learned with this is that the original conditional is not equivalent to either one of these. So you can't simply just put a not in front of both and have it be the same thing. That's not true. You can't switch them and it be true. Okay, there was a fourth one though, contrapositive. All right, and that was if you did both of these things, if you switched them and you put a not. So if not Q, then not P. Right, and that one is logically equivalent. So the conditional statement, the original, is logically equivalent to the contrapositive. These are the same. All right, so let's use that. Now we're actually going to start with the contrapositive. I'm going to start with the negative version. So what this is saying is that if f is not continuous, so we're going to write this here, if f is not continuous, then f is not differentiable. That's what we just learned in this section of our notes. Okay, well, what I'm saying is that if we do the contrapositive of this, that we will get a statement that's logically equivalent. All right, so let's write the contrapositive of this. If f is differentiable, so I'm taking away the not and I'm switching them. If f is differentiable, then f is, once again, taking away the not and switching them, then f is continuous. This statement that I just wrote right here, very important that you have that connection. Okay, if you know that a function is differentiable, then you also know that function is continuous. Because if it was not continuous, then it would not be differentiable. All right, this is a statement, the one I just circled here, that we will use a lot in our free response questions. Okay, so you definitely want to have that in your head. I wanted to go ahead and talk about it now. All right, so the third way that you can have a function be not differentiable is if there is a vertical tangent. So right here, there's a vertical tangent line, probably more on the axis right there. There's a vertical tangent line. So we would say f is not differentiable at x equals 1 because there is a vertical tangent at x equals 1. Again, f is differentiable for all other values of x. So it's just this one location where the derivative does not exist. All right, I will say that number 4 and number 1 often are included in the same spot. So a lot of people will say there's just 3 ways to identify discontinuity. And that's because it looks very similar. A sharp turn, you have this turn going. A cusp is when 2 curves meet each other like that. All right, so this has a cusp at x equals 1, and you would say f is not differentiable at x equals 1 because there is a cusp at x equals 1. Okay. Test for differentiability. So you will use the alternative form of the definition of derivative, which we learned about in our last lesson. There it is again, to test whether a function is differentiable or not differentiable. All right, so if f is differentiable at a point, then that means that the limit, this definition of derivative from the left side will be equal to. So if f prime exists, and I'll put in parentheses, if f is differentiable, then the limit as x approaches c from the left of f of x minus f of c over x minus c will equal the limit as x approaches c, x approaches from the right of f of x minus f of c over x minus c. All right, let's do that on these problems. All right, so we have this function at c equals 3. Okay, you could graph this out. Okay, let's graph it out over here. So c equals 3 gives me 0. So I know at 3 there's a 0 there. All right, then let's just plug in a couple points to the right and a couple points to the left. So if I plug in 4, I get 8 minus 6, which is 2. If I plug in 5, I get 10 minus 6, which is 4. If I plug in 2, I get 4 minus 6, which is negative 2. Absolute value turns that into positive 2. And if I plug in 1, I get 2 minus 6, which is negative 4. Absolute value turns that into positive 4. So I have my shape going like that. We are looking at this where c is equal to 3. So you should know from our front page that f is not differentiable at c equals 3 because it has a sharp turn there. So that's one way that we could explain how we know that this is not differentiable. Okay, the problem specifically told us, though, use the alternative form of the derivative. Okay, so we're going to do it that way. So what's going to be helpful here is we're going to rewrite f of x, and we're going to rewrite it as a piecewise function. Okay, remember that the absolute value functions equal to whatever's on the inside as long as your x values are greater than or equal to whatever number makes this 0 inside here. So we know that that's 3. And then your absolute value is equal to the negative version of whatever's on the inside whenever x is less than that same number. Okay, so now we're going to use the alternative form of the definition of derivative. So we're going to do the limit as x approaches 3 from the left. 3 is our c value, of f of x. So if we're approaching from the left, we're on the bottom piece because that's where x is less than 3. So negative, parentheses, 2x minus 6, then minus f of c. So what do you get when you plug the number in? We get 0 over x minus 3. All right, if I plug in 3 right now, I get 0 over 0. So we're going to do a little algebra here. I can take out a 2. So this is equal to the limit. Actually, let me go this way. This is equal to the limit as x approaches 3 from the left of negative 2 times x minus 3. We can get rid of that minus 0 divided by x minus 3. The x minus 3's cancel, and the limit of a constant is equal to the constant. So that limit's equal to negative 2. All right, now let's do the limit from the right. The limit as x approaches 3 from the right. Now we're on the top piece because we're greater than 3 coming from the right. So we get 2x minus 6 minus f of c. So if you plug in 3, what do you get? You get 0 divided by x minus 3. Okay, this is equal to the limit as x approaches 3 from the right. We're going to take out a 2. It's going to leave me with x minus 3 divided by x minus 3. The x minus 3's will cancel out. Limit of a constant is equal to the constant. For the derivative to exist, those two limits have to equal each other. All right, so we would say f is not differentiable at x equals 3 because, and we're going to use our limit notation, because the limit as x approaches 3 from the left of f of x minus f of 3 over x minus 3 does not equal the limit as x approaches 3 from the right of f of x minus f of 3 over x minus 3. All right, so our next one, this one's a little harder to graph. So we're just going to start straight from the alternative form of the definition of derivative. We're going to do the limit as x approaches 2 from the left of f of x, which is x minus 2 to the 2/3, minus f of c, or f of 2. So if I plug in 2, I get 0, and over x minus 2. All right, so on this one, let's see. We can, since they have the same base, I can ignore the minus 0. They have the same base, so I can subtract the exponents. 2/3 minus 1. That would give me negative 1/3 and would go on the bottom. So this would be the limit as x approaches 2 from the left of 1 over x minus 2 to the 1/3 power. Okay, so now if I plug in 2, I do get 0 on the bottom. So I know that this is going to go to either infinity or negative infinity. So if I'm coming from the left side, I'm plugging in numbers smaller than 2. So that would give me a negative number. And since this is an odd exponent, it's going to stay negative. So I have a positive divided by a negative. That's going to make that negative infinity. All right, let's do the same thing from the right side. The limit as x approaches 2 from the right of x minus 2 to the 2/3 minus f of 2, which is 0, all over x minus 2. So same process here. Limit as x approaches 2 from the right of 1 over x minus 2 to the 1/3 power. And then now if I plug in numbers from the right of 2, they're numbers that are bigger than 2. And so a number bigger than 2 minus 2 would be a positive number, and a positive over a positive is a positive infinity. All right, and so now we can say that f is not differentiable at x equals 2 because the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2 does not equal the limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. All right, one more. So we have a piecewise function. So this is set up nicely for us. We're trying to investigate c equals 1. So if you think about it, this is a parabola, and it's always continuous and always differentiable. This is a linear function, and it is always continuous and always differentiable. If you think about those two and what they look like, they don't have any sharp turns. They don't have any discontinuities. They don't have any vertical tangent lines. So none of those things we're looking for things to be not differentiable exist. So the only possibility for these to be not differentiable is at the number where they connect to each other. Right? That could be a sharp turn of some sort. They could not connect at all, and it'd be a discontinuity. Okay, so that's what we're looking for here. All right, so we're going to do the limit as x approaches 1 from the left of f of x. So that's the top function, x squared plus 2, minus f of 1. So if I plug in 1, I get 3. I have to plug it in down here because this is where we have the equal sign. So 3 times 1 is 3, over x minus 1. All right, so that's going to be the limit as x approaches 1 from the left of x squared minus 1 over x minus 1. I have a 0 over 0 situation still, so let's do some factoring. So that's going to be x plus 1 times x minus 1. And the x minus 1s will cancel. And 1 plus 1 is 2. All right, then we're going to do the limit as x approaches 1 from the right. All right, so from the right, we're going to have the bottom function. That's where x is greater than 1. So we have 3x minus f of 1, which is 3, over x minus 1. Again, this is a 0 over 0, so we're going to do some factoring. So I get 3 times x minus 1 over x minus 1. The x minus 1s cancel out, and the limit of 3 is equal to 3. My limits are not equal to each other, so I would say f is not differentiable. At x equals 1, because the limit as x approaches 1 from the left of f of x minus f of 1 over x minus 1 does not equal the limit as x approaches 1 from the right of f of x minus f of 1 over x minus 1. All right, there is a possibility on this problem that we could have gotten two numbers that are equal to each other, and then we might have said that the f is differentiable. Okay, and it's possible that that answer could have been wrong. Okay, so anytime you have a piecewise function, you want to also check if it's continuous. So I probably should have done that first, but since we already did the work here, I'm just going to do the continuity off to the side. So with continuity, we do the same thing, except we just do the limit from the left and the right of the original functions. We don't do this whole f of x minus f of 1 over, that's for the derivative. This difference quotient is because we're doing a derivative. Okay, when you're doing continuity, you're just using the function. So I'm going to put continuous, question mark. All right, so let's do the limit as x approaches 1 from the left. So if I'm coming from the left, I have the top function, x squared plus 2. And that's equal, I can just plug in 1. 1 plus 2 is 3. And then I do the limit as x approaches 1 from the right. So from the right would be the bottom function, so that'd be 3x. And I plug in 1 and I get 3. So since those agree, and I also, if I plug in 1 to the function, I get 3 as well. So I would say f of 1 is equal to 3. All right, so since all three of those are the same number, then I would say that f is continuous at x equals 1, because the limit as x approaches 1 of f of x is equal to f of 1. Okay, I know that this limit exists because the limit from the left and the limit from the right equal each other. And then I know that it's continuous because that limit equals the value of the function. So this is not differentiable, but the reason is not because it's not continuous. It is continuous. So it's not differentiable for another reason. Most likely, actually not even most likely, for sure, because the slopes are different on the left and right side, there's a sharp turn when these connect to each other. All right, I will see you guys on the next video.